On the darkest of nights, free from the glow of the moon and the haze of light pollution, a stunning formation can be seen imprinted upon the sky. Ancient African observers knew it as the backbone of the night, while Polynesian sailors thought it was the jaws of a cloud-consuming shark. The ancient Greeks believed it to be a stream of milk, spilled from the breast of the goddess Hera, which they called Gala, a term that eventually gave rise to the word galactic. This gave us the name for our galaxy, the Milky Way. Our galaxy is a giant that extends for hundreds of thousands of light years, yet its structure is more dynamic and evolving than we ever could have known. Thanks to the revelations of one particular mission, we are finally starting to unravel the great mystery by tracking the paths of stars, allowing us to extrapolate our galaxy's past and reveal the history of the Milky Way. If you like what you see today, please consider subscribing to help the channel. Otherwise, sit back and get ready because it's a hell of a story. #### our home galaxy. The Milky Way is an ancient, enormous barred spiral galaxy, with a peanut-like bar of densely packed stars at the core, surrounded by a series of swirling filaments of younger, hotter stars and gas. This spiral structure forms the thin disk component of our galaxy, which stretches just over 100,000 light-years. But the true size of the Milky Way extends well beyond this visible component. Enveloping the thin spiral disk is a larger thick disk of more eccentric stars, rising thousands of light-years above and below the spirals. Even further beyond, we find the Milky Way's enormous galactic atmosphere, a diffuse halo of stray stars, gas, and plasma, along with its ancient clusters and satellite galaxies. The Milky Way houses at least 100 billion stars, possibly as many as 500 billion, with just as many planets. Earth is one of those planets, located 28,000 light-years from the galactic nucleus, taking around 230 million years to complete a full orbit. Stars farther from the galactic center can take up to 700 million years, while objects in the halo may require 1 billion years to orbit. In reality, the Milky Way is far from the synchronized celestial clockwork we perceive. The so-called spiral disk structure is more like a great galactic ocean, with each of its arms the consequence of a gravitational ripple, echoes of seismic events in the galaxy's past. By measuring the movements of stars caught in these ripples, we can reverse engineer them to reveal insights into the Milky Way's history. By charting the positions and velocities of stars in our galaxy, we can plot their paths through space, allowing us to extrapolate both their past and future trajectories. The more stars we can probe for such properties, the greater the dynamic picture of the Milky Way we can build. Thus, astrometry, the science of measuring the positions of stars, remains at the forefront of our quest to map the Milky Way. According to traditional models, in the earliest times before the epoch of galaxy formation, newly formed stars and gas concentrated within large, bubble-like gravitational wells of matter. These attractors laid the foundation for galaxies, much like the groundwork for a skyscraper. Over billions of years, stars and gas accumulated and flattened into orbit around the core of these wells, eventually forming a neat, cartwheel-like spiral structure that emerged billions of years later. Indeed, we observe these ancient objects grouped into globular clusters, dense cities of early stars, containing anywhere from 100,000 to a few million stars. These stars formed together at the same time from the same collapsing cloud of matter. Some of these clusters may be as old as the Milky Way itself and are thought to have gathered in the galactic halo during its early stages of formation. This makes them perfect fossils, whose velocities and movements can be traced back more than 12 billion years. Their far superior size and brightness compared to the average star allowed Gaia to map the movements of more than 150 distant clusters with remarkable precision. #mapping the Milky Way. In the 1990s, the European Space Agency's Hipparcos satellite represented our best effort in this endeavor. The star mapping probe spent 3.5 years tracking bright stars to observe their movements through space. By 1997, its findings were compiled into the Hipparcos catalog, listing 118,000 stars with high precision and 1 million more with lower precision. By the year 2000, improved data techniques had expanded this number to 2.5 million stars, including 99% of the galaxy's brightest. Then, in 2013, ESA launched Hipparcos' revolutionary successor, the Gaia spacecraft, which measured properties of more than 1.2 billion stars with unprecedented precision. Gaia's first complete data release came on April 25, 2018. In the months that followed, scientists used the massive dataset as the basis for supercomputer simulations, which recreated the Milky Way's development. These simulations uncovered astonishing revelations from its past. As we mentioned earlier, beyond the visible thin disk lies a giant, diffuse galactic halo of matter, which scientists believe was the first part of our galaxy to form. According to traditional models, before galaxies fully formed, newly formed stars and gas concentrated within large, bubble-like gravitational wells. These wells laid the groundwork for galaxies, like the foundation for a skyscraper. Over billions of years, stars and gas collected and flattened in orbit along a common plane around the heart of the halo, eventually giving rise to the neat, spiral structure we see today. Thus, the galactic halo was the first part of the Milky Way to take shape, and it's where we expect to find its oldest stars. Indeed, we see ancient objects clustered in the galactic halo, forming globular clusters, groups of early stars containing anywhere from 100,000 to several million stars that formed together from the same collapsing cloud. These clusters, some as old as the Milky Way itself, serve as fossils, whose movements can help us extrapolate the galaxy's history over 12 billion years. Thanks to their size and brightness, Gaia was able to map the movements of more than 150 distant clusters with great precision. In 2020, this data was fed into the eMosaic's neural network, which simulates a spiral galaxy's environment and evolution. By grouping the clusters according to common velocities, the simulations revealed a far more dynamic and unstable history for our galaxy than previously imagined. Even before Gaia, scientists suspected the Milky Way had a violent youth, but they didn't realize just how violent. The eMosaic simulations attributed the majority of the Milky Way's structure to 5 significant minor merger events. During these events, the young Milky Way collided with and devoured smaller galaxies, assimilating their stars and gas. While 4 of these merger events were previously known, one took astronomers by surprise. Likely the oldest and earliest merger, this event involved a progenitor galaxy named Kraken. Kraken is believed to have been the first large galaxy consumed by the Milky Way, colliding around 11 billion years ago when the universe was less than 3 billion years old. Back then, the Milky Way was far smaller, with less than a quarter of its present-day mass and no spiral structure. Kraken's collision brought more than 100 million stars into the Milky Way, marking the most significant collision in our galaxy's history.